So why do commercial jets fly high? Is it purely in the interest of economy, or is there more to it? Let's find out in today's video. Welcome back. In this video we will be learning why it is advantageous for commercial jets to fly high. Commercial jets typically fly within a certain altitude range, and this is predominantly due to the efficiency of the engines by design. Now, before we talk about this any further, let's digress for a moment and understand the effect of drag on an airframe and how this has a bearing on the preferred altitude. You see, jet aircraft have low drag because they are designed to fly fast. They have comparatively thin wings, a streamlined shape, and all the design philosophies necessary to keep all forms of drag to a reasonable minimum. If you watched the video that explains how lift is generated, you might recall that one of the four forces acting on an airplane is drag, which is the resistance to motion. Now let's dissect that a bit more to understand the different types of drag. All of this against the backdrop of flying higher and faster. An interesting fact about drag is that there are several types of it, and they vary with the airspeed. Let's look at each of them. So the first type of drag we have is induced drag, which is an inevitable consequence of the wing generating lift. Induced drag is most dominant at low speeds, when the aircraft needs to fly at a relatively higher angle of attack to maintain lift. The angle of attack is simply the angle between the airfoil or the wing and the relative airflow. And why does the angle of attack need to be increased as the speed decreases? Well, quite simply, the coefficient of lift, or CL, which is one of the components in the lift formula, is a function of the angle of attack. And if the airspeed decreases, then to maintain the same amount of lift, the angle of attack needs to be increased, which in turn increases the coefficient of lift and therefore helping achieve the same amount of lift. And as the angle of attack increases, a byproduct of that is the creation of stronger vortices. Now, in case you're wondering what vortices are, wingtip vortices are counter-rotating spiral bands that emanate from the back of the wing as a result of the generation of lift. And as the wings create stronger vortices as a result of flying at a higher angle of attack, this actually leads to a slight backward component in the lift vector. And this is exactly what creates induced drag. The second type of drag we have is parasite drag, which is drag posed by the forces that work to slow an aircraft's movement. As the term parasite implies, it is not associated with the production of lift. Very quickly, parasite drag is actually made up of three types of drag, namely skin friction, form, and interference drag. Now, we wouldn't actually get into what those types of drags are, but just a high-level overview for you. But quite simply, think of parasite drag as a resistance posed by the airframe itself. Now, parasite drag varies directly with the indicated airspeed, and it increases as the airspeed increases, as we can see in this little diagram. So to summarize, as the airspeed increases, the angle of attack decreases to generate the same amount of lift, parasite drag increases and induced drag decreases, and vice versa. And so it can be seen that parasite drag and induced drag are inversely proportional to one another. Having talked about the two types of drag, it can now be inferred that the total drag of an aircraft in flight is the sum of induced drag and parasite drag. And the illustration here shows the variation of total drag with the indicated airspeed. Now, having looked at the different types of drag and how they act on an aircraft in flight, let's circle back to why it is advantageous for aircraft to fly higher. Since drag in terms of speed varies only with the indicated airspeed, an aircraft flying higher at the same indicated airspeed would have a higher true airspeed, which is the speed corrected for air density. Now, to explain it simply, as the aircraft climbs, it encounters lower air density. And so effectively, it becomes necessary to fly faster to experience, let's say, the same amount of air molecules of the wing to generate the required amount of lift. The indicated airspeed doesn't change that much, since it's a measure of the pressure being experienced by the airframe. However, the true airspeed of the aircraft does increase as an aircraft climbs, as it compensates for the lower air density. Now, since drag is a function of the indicated airspeed, not the true airspeed, at higher altitudes where the true airspeed is greater because of the lower air density, more miles are covered for the fuel expenditure necessary to produce the thrust to equal the drag. In other words, the drag may not have changed much when comparing lower altitudes to higher altitudes, but because the aircraft does end up flying faster at higher altitudes due to the lower air density, and so lesser resistance posed to the airframe, it actually travels faster for the same amount of drag, more or less, therefore making the flight more economical. So this is one of the reasons why there is a need to fly higher. The other reason jet aircraft fly high is simply because jet engines are designed to be most efficient at high altitudes. Jet engines gain an efficiency benefit when they run close to their maximum RPM limit, or the maximum exhaust gas temperature limits. Because remember, jet engines are heat engines, something we discussed in the previous video. And flying at higher altitudes makes it possible for jet engines to be run at higher RPMs to compensate for the lower air density to generate the same amount or the required amount of thrust. Something that wouldn't be doable at lower altitudes, because if the engines were operated close to the maximum RPM in level flight at low altitudes, the aircraft would quickly exceed its maximum speed limit. Alright, so there we have it. Why commercial jets fly high. You see, aircraft just cannot keep climbing, as there is a maximum altitude which they are certified for, also known as the ceiling. And this ceiling is determined by performance and aerodynamic limitations, also known as the coffin corner, and it is something we will explore in a future video. But I hope that made some sense and it wasn't too difficult to follow. As always, if you have any questions, comments, suggestions, or you would like a certain topic related to aviation or flying covered, please put that in the comments below and I shall do my best to cover that in a future video. If you liked the video, please give it a thumbs up and share it along. Well, thanks very much for your time and support, and I look forward to seeing you in the next video, where we shall explore the subject of coffin corner. Thanks very much again, and I wish you a great day.